Hello everyone. So today we are going to discuss about and electric flux and relation between electric field and electric flux and their formulas and their concept and then electric flux due to a charge. So basically we are going to discuss electric flux. So electric flux basically gives the idea. Suppose electric for understanding electric flux, let me understand first here thing. Suppose here electric field lines going in this direction and you put some random surface on this surface, right? So on this random surface, how many total number of electric field lines crossing that surface, that defines the electric flux. And so we can define now means how many electric field lines passing from this surface, that defines the electric flux. So we can write the definition for electric flux. Basically electric flux represents the total number of electric flux basically electric flux basically represents represents the total number of electric field lines electric field lines crossing total number of electric field lines crossing the surface in a direction normal to the in a direction normal to the surface. This defines electric flux. And basically electric flux is a scalar quantity, right? And it is denoted by phi, right? So now main task here, we require area vectors. So first we can understand that what is area vector. Area vector is basically a vector quantity that will help us to determine the area, how many number of electric field lines passing through that area. Suppose I just take some example. Suppose electric field lines passing from that surface. This is electric field lines passing from that surface, and this surface has a area vector that is normal to the surface is like this. So here you see, and suppose I take some other, this is a square, so that has a area vector in this direction, right? And one more thing, this is a sphere. Make just 1 minute. This is a sphere, so their area vector, suppose I take here one surface, so their area vector is outward normal to the surface. So area vector is a vector quantity and it is always normal to the surface. If I take closed surface, area vector is always outward normal to the surface. Right? Now, now we can define the relation between electric field and electric flux. So that we defines by the quantity phi, that is equal to surface integral of electric field vector dot area vector, that is electric flux, that is we define by electric flux. So surface integral of a electric field over that surface we defines by electric flux, right? And unit of and one more thing, this is a dot product a dot b vector, that we can write as ab cos theta. So we can also write here this as phi is equal to eda cos theta, right? Now unit of unit of electric flux, unit of electric flux is basically Newton meter square per coulomb, or basically second is volt per meter, and another is dimensional formula. Dimensional formula also we can write as, that is ml t की power -2 l square and ampere. So we can write as mlq t की power coulomb is m, basically charge is I into t, I into t, I into t, mlq t की power minus q, that is a inverse, right? And then after that, now we are going to solve some problem so that we can understand this concept more better way. So I give some, this is a surface, right? This is also a surface, this is also a surface, this is also a, so I take some example so that you can understand more better way, right? So here I take example. So here you see electric field lines is like this, here electric field lines like this, here electric field lines like this, and here electric field lines like this. Now here you see area vector, you draw normal to the surface. For this area vector normal to the surface, here area vector normal to the surface, and here area vector normal to the surface. So for this we can write flux that, and this is electric field, this is electric field. So here you see this is theta. So for first case phi is equal to E A cos theta. For second case, here theta is the angle, And one more thing, here you can also write theta is the angle between electric field and area vector normal to the surface. Right here, so he can write here phi is equal to E A. For this case, we can write phi here theta is equal to 0 degree. For here, theta is equal to electric field and area vector direction is, because this is electric field and this is area vector, so that angle is 90 degree. So here E A cos 90 degree. So that is, we can write as a E A. Here you see electric field and area vector has an angle 180 degree. So here phi is comes out to be EA cos 180 degree. So that is comes out to be minus EA. Right? So you are able to understand all these things. So now we are going to proceed and do some other problem. This concept, if you are able to understand, so I give one more problem so you can get more idea about electric flux. So this I take cylinder, this is our cylinder, and here outward normal flux. So here what you see, here electric field lines passing from this cylinder, right? So now you have to find, this is first surface, this is second surface, this is our third surface. You have to find electric flux through all these surfaces, right? And these are our electric field, lines. So you have to find electric flux through all these surfaces. So first task, what we do, we have to first find electric field direction and area vector direction. So here you see area vector direction is here away from the surface, and here you see area vector direction is away from the surface, and here you see area vector direction away from the surface. So first we can find here you see electric field in this direction and area vector in this direction. So this has an angle of 180 degree. Here you see here electric field direction and area vector direction has a 0 degree, and here you see electric field direction and area vector direction is 90 degree. So for this surface flux is minus EA. For this surface flux is EA. For this surface flux is G. And one more thing we can note down, for closed surface, for closed surface outward flux is taken to be positive, and for closed surface outward flux is taken to be positive, and inward flux is taken to be negative, right? Now our next task, here just we can show by diagram also. So here area vector and electric field vector are normal to the surface. So here positive flux and here electric field lines coming into the surface. So here we taken as a negative flux. Now next we can also complete it, electric flux due to a charge. Electric flux due to a charge. Here we can see first part we can see electric flux due to electric fields, and then next part we can see electric flux due to a charge. In next part we have seen electric flux due to a charge. So now here you see electric flux due to a charge. So basically we discuss in three cases. For this electric flux due to a charge, in first case we see charge inside the surface, charge outside the surface, and charge inside and outside the surface in both cases. So case you see charge inside the surface. So here you see this is charge Q and this is radius R. So we have to find electric flux due to this charge. So we know that this is a sphere and we have to find electric flux due to this charge. So first what we do, we draw. First we can find electric flux due to this small surface, and then after that we can integrate and find that how much electric flux passing from this surface. So we know that electric field due to this charge outside is 1 upon 4 pi epsilon naught kq by r square r cap, and we know electric flux is equal to E dot ds vector, that is area vector and electric field vector, both are in same direction. So angle is 0 degree. So can I write here E dA, right? And here you see d phi is equal to kq 1 upon 4 pi epsilon naught q by r square into dA. Now here you see phi is equal to integration, this is a closed surface, so d phi, that is comes out to be closed surface 1 upon 4 pi epsilon naught q by r square into dA. So phi is equal to 1 upon 4 pi epsilon naught q by r square into dA. So this is a closed surface and surface area of a sphere, that is comes out to be 1 upon 4 pi epsilon naught q by r square into 4 pi r square. So 4 pi cancel, r square cancel, so that comes out to be phi is equal to q by epsilon naught. This is also we say Gauss law. Gauss law. So from here we can conclude that the total charge inside a closed surface, that is equal to, so we can conclude from here, we can also conclude that total charge enclosed inside a closed surface, that is equal to charge enclosed, total electric flux of the room, a closed surface is equal to charge enclosed divided by epsilon naught. So phi is equal to q inside divided by epsilon naught. So what is they are telling, I just give some example. here you see. So here I take 1 plus q charge, q1 charge. And one more thing here, important points is that this is independent of charge location and independent of charge location. Independent of charge location. That means you put anywhere inside a closed surface, that always equal to q by epsilon naught. So here if I put q1 plus q1, here minus q2, here plus q3. So if I have to write for total electric flux, that is equal to q inside, that is plus q1 minus q2 plus q3 divided by epsilon naught, right? Now we move for second case. Case second, charge outside the closed surface. Charge outside the closed surface. So here you see this is q and charge going outside. So here we can see that total electric flux, we have just seen that incoming flux is be taken as a negative. So this is a surface. Here you see. So charge incoming, phi inside be taken as minus phi, and charge going outside plus phi. So can I find phi total? That is comes out to be phi inside plus phi outside, that is minus phi plus phi, that is comes out to be phi total is comes out to be 0, right? So now for our third cases. So from this we can conclude that if I put charge outside from here, conclusion is that if I put charges outside, their net electric flux will be 0. So I take some examples so that you can understand more better way. Suppose this is a closed surface. If I put here plus q, here minus q, here plus 2q. So if I ask you total electric flux through it, that is 0. So charge outside the surface, their electric flux always comes out to be 0. Now for case third, we can see case third, charges inside and outside, inside and outside a closed surface, inside and outside a closed surface. So here you see some charges inside, minus q2 plus q3 plus q4 minus q5. So if I ask you total electric flux, so we have already seen in previous case that charge outside the closed surface, their net flux is always comes out to be 0. So we have to only consider inside the closed surface. Total electric flux is always only comes out to be plus q1 minus q2 by epsilon naught. So that's it. So I hope you will understand all these my cases, and you tell me how you feel my uh, explanation. And if you have any doubts coming, or if you want more lectures on any other topic, you can comment on it. Okay, so we will meet in the next lecture. Hope you we will do more problems in the next lecture. Bye.